Hello, Algebra students. This lesson from our unit on functions is going to be all about features of graphs. I do have a warm-up question on the screen, so I encourage you to go ahead, pause the video now and see if you can answer it, and come back to the video once you want to check your answer. Okay. The warm-up question is asking you to describe Diego's trip walking home from school in your own words. When you are describing a graph, some of the things you might mention are some of the numbers you can see from that graph. So for example, in the past, I've had some students mention how far away he is when he starts. That y-intercept or that vertical intercept is telling you his starting point. So you might say that he starts, it looks like I'm going to go with 2.5 because it looks like it's right in between 2 and 2.5. So we could say he starts 2.25 kilometers from home. So that must be how far away his school is. How do we know he's walking home? How do we know that he's not walking further away? Well, my y-axis says it's kilometers from home. And so I notice the line is going down. And so that means his distance from home is getting smaller, which means he must be going towards his home. So we could say he walks home. You can also from this graph get a speed, and it doesn't have to be like a specific number. Like I might not be saying he's walking home at 10 kilometers per hour or something like that, but we can describe if the speed is constant, meaning the speed is remaining the same, or if it's changing, if he starts walking slow and then increases his speed or decreases his speed, something like that. And looking at this graph, because we have that straight line, that means he's going the same kilometers for every chunk of time. So that means he's walking home at a constant speed. And then there's one other thing I might mention, and that is my x-intercept here. What do you think that point's telling me? It's telling me two things. It's telling me the kilometers from home at this point is 0. So if he's 0 kilometers from home, it means he is at home. So I could say he gets home. And then I can also include that time. So I could say he gets home after 20 minutes, something like that. What we did in this warm-up is what this lesson video is going to be all about. Looking at some more complicated graphs, but talking about which features of the graphs are most important to look at and what information they can tell you about the story or situation. So jumping right in, this is our goal, is to use features of graphs of functions to learn about situations. For this first one, I've got this graph here that shows two functions. And let me move my face just a little bit. That didn't do much. I can put my face up here. The graph over here has two functions on it. One is a toy rocket and one is a drone. And if you're unfamiliar with these, I've got pictures of both. A toy rocket looks something like this, where it's going to shoot up in the air and then gravity will be bringing it back down. And then a drone is more like a toy, an electronic, where you can see kind of over here, it's very blurry, but there's a person who controls the drone with a remote, and the drone is going to go up and down and forward depending on what that person with the remote tells it to do. So looking here, we have this graph, and we've got here are the graphs that represent the heights of the two objects as a function of time since they were launched. I do notice we've got that phrase, a function of, so it's telling me that the height of the objects, because it comes first in that phrase, that is our output. And sure enough, if you look at the graph, our height is right there. And then it's also telling me time is the input. And sure enough, their time is on our x-axis. We're also told that height is measured in meters above the ground and time is measured in seconds since the launch. What we are going to do with this graph of these two functions is this right here. We are going to analyze the graphs and describe as precisely as we can what is happening with each object. We want our descriptions to be as complete and precise enough that someone who is not even looking at the graph could visualize how these objects were behaving. My plan for this question is I'm going to model and give one as an example of what your description might look like, and then have you try the other one. And the one I'm going to talk about is function R here, which represents that rocket. Similar to what we did during the warm-up with that graph about Diego walking home from school, when I'm looking at this graph here, I want to mention everything I can. That's what it means by being as precise as possible. So the first thing I want to mention is our starting point, where our line begins. And I also want to be thinking about what does that mean in the story. So I don't want to just say the line begins at this number, but talking about specifically the rocket and what that beginning point tells me about the story. So starting right there, it's in between 20 and 30. So that's going to be the number 25. And I can start by saying the rocket begins at a height of 25, what are we measuring with? 25 meters. So that must mean the rocket isn't on the ground, right? It's on some raised platform. Maybe someone's shooting it from something high up, like maybe the roof of a building or something. But it's definitely starting not on the ground. So we've got it starting here. And then I want to describe what comes next. What I notice is that my line is going up like this. And it's curved, so it's different than that graph we saw in the warm-up with Diego. This would not be a constant speed. It goes up a lot in the beginning, and then it starts to flatten out, which means the height isn't getting as high near the end of that line. So I could say the height increases. I'm going to say after it was launched. Launched means like shot up in the air. We're seeing that word here. So the height increases after it was launched. And let's put some numbers to this. So you might tell me how high up it gets. You might tell me how long the height is increasing before it starts to not increase. I'm looking at the graph and it looks like around here is where it stops increasing. So I'm going to estimate that as 2 seconds and about 45 meters. So I'm going to say the height increases after it was launched for 2 seconds until it reaches a height of, 45 meters. There are a lot of different ways you could say this. You might say that the drone reaches its highest point 2 seconds after it was launched at a height of 45 meters. You could say that's the maximum height. There's no one correct way to write this by any means. After that point I have in pink, what starts to happen? Well, our line is curving, but this time it's going down. And I'm constantly, again, thinking of these words here, height and time. So time's going on, and our height is going down. That means the toy rocket went up, and then after a certain point in time, it starts coming down. So now I could say the height is decreasing, but I'm going to use the words falling. Our toy rocket is now falling from the sky. So I could say, then the rocket starts to fall until there's one final point I want to mention. It starts to fall until when? Well, it's going to keep falling until this point here. Go ahead and see if you can describe that point I circled in yellow. What happens? It's at the number 5, so we're talking about 5 seconds. What happens at 5 seconds? Well, that's where the height is 0. Think about what it means if the height is 0. If your height is 0, that means you are on the ground, or not you, but this rocket. So we could say, then the rocket starts to fall until it reaches the ground at 5 seconds or 5 seconds after launch, something like that. I've got mine all color coded so you can see where I'm getting each piece of information. Like I said, in a moment, you're going to do the same thing for the second function here. But I think this is a really strong example. We're mentioning all the important numbers, and we're mentioning each time the rocket changes what it's doing, right? We've got the height was increasing and then decreasing. We also mentioned the starting point and the stopping point. And when we mentioned those, we didn't just say like it stops at 5 seconds, right? We're really thinking about the story and what it would mean. I'm not saying the height is 0. I'm saying a height of 0 means it's on the ground. So this right here is my example. I'm going to ask you, go ahead, pause the video now and see if you can do the same thing for our second function, the one labeled D for that toy drone. Come back to this video once you're ready to check your answer. All right, hopefully you came up with a description for our graph of our drone. I've got up on the screen an example of what you might say. Like I said earlier, there is no one correct answer for how you would describe this. How I described it is I've got it starting on the ground. I know that because our line starts here at 0. So similar to what we had said for that last one, if the height is 0, that means it is on the ground. So that's where I got this information. It starts on the ground and it rose. It's going up at a constant speed. I know that the drone is going up because if I look at this, my height here is increasing. And I also know it's a constant speed for the same reason we knew Diego on the warm-up was walking at a constant speed. We've got that straight line. So notice you're going up 10 meters every second, another 10 meters every second. I've had students even say, like, the drone rises at a speed of 10 meters per second. You can do that. That is very specific. But really focusing on those words like constant speed is good. And we know that because we've got that straight line. It's not curving the same way our rocket did. I also mentioned the specifics for that point right there. And so it was rising at a constant speed until 2 seconds when it got to that maximum height of 20 meters. Once it got to the 20 meters, this part right here is interesting. We didn't have this with our rocket. If I look at that yellow part, notice at 2 seconds, it's at a height of 20 meters. At 3 seconds, it's at a height of 20 meters. 4 seconds, height of 20 meters. What is that drone doing? Well, you've got some options. I described it as it's maintaining its height. It's keeping the same height. It might do that, though, for a variety of reasons, and we can't tell from this graph. The person controlling the drone might have it go up and then just stay there in the air, right? So it's just hovering. It's maintaining that exact location. Or the person controlling the drone could have had it go up and then maybe had it like move forward in the air. And so if it's moving forward in the air, it's maintaining that same height. It's staying at that height of 20 meters. So you might have said it stopped or it stayed in the same spot at 20 meters, or you could have said it was moving forward at 20 meters. It's hard to really know from what we're looking at on our graph. I use the word maintain its height for 3 seconds. Now, sometimes people ask, why is it 3 seconds and not 5 seconds? Notice it stops right here at 5 seconds. Well, it started at 2 seconds. So from 2 to 5 seconds means it was maintaining its height for a total of 3 seconds. And then our final part, I notice my line is going down. So my height is decreasing. And again, it's that straight line. So we've got that constant speed. So I said it's lowering back to the ground, and it took 2 seconds to do that. I know it's going back to the ground because by that 7, it's back to a height of 0. Like I said, this is just one example of how you could have worded it. What the hope is after looking at these two graphs and these two descriptions is this part right here. When you're looking at these graphs of these functions, what parts of the graph or what features of the graph show the most important information. When we were trying to describe these graphs, what did we really focus in on? For example, in that description we just looked at, I didn't mention that at 1 second the drone was at 10 meters. That point right there isn't really one of the features that I'm focused in on. Any ideas of what features we might focus on? In the past, and especially since if you're coming from pre-algebra and algebra 1A, we're really used to talking about these points right here, our y-intercepts, or you might also hear them called vertical intercepts. Those are always important features to look at. Along with those, these right here, your x-intercepts or your horizontal intercepts are also always good ones to make sure you're focused on and describing in these descriptions. In addition to that, we also mentioned this point right here and this section right here, which is your maximum. Maximum is that highest point. And along with that, you might also mention any minimums you see on that graph. Here, our minimums were just these points down here on our x-axis, so we didn't describe them twice. But if the graph looked different, you might also mention a minimum there. And then finally, we really focused in our descriptions on what direction the line was going. So you might want to mention if that line is increasing, if it's going up, or when the line is decreasing. All of that tells you specific information about what's happening in that graph. The increasing and decreasing is how we knew if the toy rocket was going up in the air or when it was going down. These are all features that when you're trying to make sense of what a graph is telling you, these are all important things to look at. I matched up these definitions with this picture here. If you like having written definitions of vocabulary words, here are the definitions. Minimum, remember, is just always let me change the graph I was about to draw. Minimum is always your lowest point on a graph. A maximum would be your highest point on the graph. Increasing is just when a line is going up, and decreasing is when your graph is going down. But if you want those written definitions, here they are as well. Pause the video now to copy them into your notes. There is a second part to this, and that is where we're going to connect all of these different features we are talking about to what we've been learning about function notation, your new favorite thing. And so that is what the second problem here is going to be all about. This second problem is about a bungee jump. We've got in a bungee jump, the height of the jumper is a function of time since the jump begins. And we're going to be looking at this function here. Function h defines the height in meters of a jumper above a river, t seconds since leaving the platform. I have this picture here, but I think what really communicates what a bungee jump looks like better is a video. So if you are unfamiliar with bungee jumping, here's a video to give you an idea of what story we're thinking about. So he's on this platform, he's connected, to that red bungee right there. And when he jumps, the bungee catches him before he hits the river. And then because it's a bungee, it's like a spring, so he's going to bounce up and down. You can always find more videos of people bungee jumping if you want to look at more examples. But that's what a bungee jump is. A person jumps, and then they're going to bounce because that bungee is like a spring until they finally kind of steady. And so that is what our graph here is it's showing me the height in meters of that jumper, t seconds after they jump off the platform. The first thing we are going to do is looking at this graph here. There are 5 different features of the graph we are going to focus in on. And our job is to match these 5 features of the graph to these 5 expressions or equations that have been written in function notation. As a quick reminder, when you are looking at function notation, like this one right here, h of t equals 80, remember this part here with the h and the t, that is not multiplication. That is just telling us that the function name is h. I'm just going to write name there, but function name. We've learned inside parentheses always goes what? That is our input. And then if it happens to be written as an equation, what comes after it would be your output. It might also help you if you pause and think about, in this situation, what are the inputs and outputs? Remember, your input you can always find on your x-axis. So maybe instead of x, I should put what is our x-axis, which is t, our seconds. And then your output's always on your y-axis, which here is your height in meters. So as we're looking at these, those are helpful things to remember. The first thing I'm going to have you do is pause the video and see if using this graph you can match up these 5 features to these 5 equations and expressions. Go ahead, pause the video and try to do that now. I'm going to go ahead and start by matching these 5 features to different points on our graph. The first one, the first dip in the graph, that means they're talking about like that first low point. Since we see the lines going up and down, that first dip is going to be right here. And I'm going to keep going through them and color code them all. Our vertical intercept, remember vertical intercept we said is the same thing as your y-intercept. That is going to be this point right here. And there's another one that's the same as the vertical intercept. When I teach this in person, this is usually the most confusing part for students, is the vertical intercept also happens to be our maximum. Both of those are in that same spot right there. So I'm just going to put those 2 dots right next to each other. Next, we've got our first peak. Peak just means the high point. So again, our line is going up and down, so it has peaks and it has dips. The very first peak would be right here in that area. And then finally, we've got our horizontal intercept. Horizontal intercept would be a point on this line. As I'm looking though, I'm not seeing any horizontal intercepts. If I had a point right here, that would be our horizontal intercept, but there isn't really a point down there. So I might save that one for last as I'm matching them up. If you were not able to do any of the matching earlier when I asked you to pause the video, use this as a hint and try to pause the video now and do it. Or even if you did try, you can always pause again and make sure that when you were describing these and matching them with the function notation, that you were looking at the right points. Go ahead, try to finish this problem if you haven't already, and then come back to see how you did. For me, I'm going to start with the first dip and the first peak, just because, like I said, when I do this in person, those are usually easier ones for students to start with. The first dip we said is right here. And so when I'm looking at these different ones, I'm noticing that it is before 5 seconds. So that input, what's inside our parentheses, is before the 5, like this one right here, h of 4. That's talking about where we're looking at an input of 4 seconds. That happens to be where that first dip is. The first peak I'm seeing is, it looks like it's before 10 seconds. I don't see any, though, that have a time before 4 seconds. However, I do see an output that's in this area with this last one right here. So first peak in the graph, I'm going to match with h of t equals 45. This one's a little different from the first dip because it's not describing a specific time, but it is telling me the output. And so that's how I'm matching it, is I know that output's going to be around a height of 45 meters. Next, looking through, I'm going to tackle this point right here, which we've already matched with both the vertical intercept and the maximum. The difference here, because they're both talking about the same point, but the difference is with the function notation, the maximum's really going to be communicating this is the maximum. And do you see which one of these, and I can cross them off. We've already used this one and this one. So do you see of the three remaining, do you see which one is communicating what the maximum is? That's going to be this one right here. H of t equals 80. It's not specifying a time, but it's saying the maximum, the biggest output, is at 80 meters. The vertical intercept then is going to be one of these ones with 0. Notice they both have 0 in it, so we're really trying to figure out on your vertical intercept, on your y-axis, is the input 0 or is the output 0? And it helps that we've already done this one because we're seeing that point right there, the output is 80. The input is what would be 0. If I go down to my x-axis there, it's talking about an input at 0 seconds. And so that vertical intercept is going to be this one here. And that's true for this graph, but also any graph. The vertical intercept is going to be where that input is the number 0. That must mean that this last one here is our horizontal intercept. I still have some questions about that because I don't see a point there, but like we said, if there was a horizontal intercept, it would be a point on your x-axis. And so any point right there would have an output of 0 because I'm not going up at all. It would be at 0. Now that we've matched this first part, there's one other thing we're going to do, and that's similar to what we were doing in the first part of this lesson. It's describing what each of these features tells us about the situation. So I'm going to scroll down to this next part and move my face. These are what we've already matched. So we matched the first dip with h of 4, the vertical intercept h of 0, and so on. The final thing is we're going to match each of these sets with one of these descriptions from the jump. So for example, one of these 5 features is communicating the greatest height that the jumper is from the river, and so on. Notice the first 4 descriptions are given to us, but this last one here, there's no description yet. So as you are doing this, after you fill in these first 4, you're going to have one left over. And that leftover one, we're going to have to write a description ourselves. So for example, as I'm doing this, I might say, okay, this first one's talking about the greatest height the jumper is from the river. Greatest height is talking about maximum. So for these 2 boxes here, the feature we're talking about is the maximum. And then we've already connected maximum to our equation, h of t equals 80. So those are going to stay together. You don't have to do that twice. So that's my example. Pause the video now and try B, C, and D. You can come back to the video to make sure B, C, and D are right before you do E. Go ahead and do that now. Okay. The second one is talking about the height from which the jumper was jumping. So we're focused in on where they were jumping from. And for me, that makes me think of that starting point here. So the part or the feature that we matched with that starting point and that would communicate where the jumper was jumping from is that vertical intercept. So my feature is our vertical intercept, which we said is h of 0. The next one, we've got the time at which the jumper reached the highest point after the first bounce. So if I'm thinking about that jumper, they go down and then they bounce up a little bit and then they keep bouncing. That's that first peak we had talked about. So our first peak, which we said goes with h of t equals 45. And then the next one, we've got the lowest point that the jumper reached in the entire jump. It might help to look back at that graph, but that lowest point was right here, that red one, which we matched with the first dip. And so that first dip. And that was our h of 4. So notice the final one that's left is that horizontal intercept. Horizontal intercept, which we said h of t equals 0. We want to come up with the description that would go with this story for a horizontal intercept. Now, we've already mentioned at this point, and I'm going to come back to the graph to help. We've already mentioned I don't see a horizontal intercept. In this story, in this situation with a bungee jump, what would it mean if there's a horizontal intercept? If you need to pause the video, think through that. Think through how we would describe a horizontal intercept for this graph and come back when you're ready. When I think about a horizontal intercept, I think about what it would mean, like I said, if we had one. If my graph was to actually go all the way down to here, what would that point mean? Well, I've got it at 20, so it would mean 20 seconds. What would the y-coordinate mean? Well, the y-coordinate would be 0. The output would be 0, which we've talked about that with the function notation. But what would it mean if the output was 0? Well, your output is telling you your height. And specifically, we said it's the height of the jumper above the river. So if that height gets to 0, where is our jumper? If they are 0 meters above the river, they are in the river. They have hit the water. And so that description of the jump would be about when the jumper hits the water, which in this situation doesn't exist. And thank goodness, right? If you're jumping, I mean, already that seems like a very scary situation. But if you were jumping from that height, you would not want to hit water. I know it's water, and I know plenty of people jump into rivers, but that would probably hurt, hitting the water from that high up. And so when we watched that video, remember, we saw the bungee jumper bouncing above the river, but they never hit the river. And for that reason, that's why we don't have that horizontal intercept. This is where we're going to end this lesson video. Again, this video was all about these different features from graphs. So that was this column here, and being able to understand what they tell you about the situation or story you're looking at, as well as connect it to the work we've already done with function notation. Thank you so much for watching. I hope you found this video helpful, and I look forward to seeing you in the next one. Bye.